One of the most important free radical reactions is a halogenation reaction. And typically halogenation reactions are best for chlorine and bromine. That meaning a chlorination and a bromination is more widely used. And the reason being the criteria for spontaneity, which we know to be delta G. Okay, and we know that delta G is controlled by the enthalpy term as well as the entropy term. Okay, and if you look at the reaction, the halogenation reaction, in this case the monosubstitution of hydrogen with chlorine to yield the monochlorinated product and a hydrogen halide, you can see that the delta S is 0 because there's really no change in entropy. You start out with 2 molecules and you end up with 2 molecules. So essentially the reaction will be enthalpy controlled. The reaction will be enthalpy controlled. And that's something you have to know. The reaction is enthalpy controlled. And so to be able to see why chlorination and bromination are the more widely used forms of halogenation of hydrocarbons in organic chemistry, let us consider the delta H, the enthalpy change of the reaction. Now, considering the bonds that break and form in the reaction, we can estimate delta H. We know how to calculate delta H because delta H can be calculated from the bond dissociation energies. We know that delta H is equal to the bond dissociation energy of the bonds broken minus the bond dissociation energies of the bonds formed. And that way you can calculate delta H. And so these are the bond dissociation energies for the different bonds in the reaction involving the halogenation of an alkane, in this case methane, right? And so if we inspect the delta H formation or delta H of the reactions for a chlorination, the bromination, and the iodination, we see that the fluorination is the most spontaneous. It's the most spontaneous, right? And it's also the most exothermic and dangerous. That when a reaction produces significant amount of heat, you know that it's going to be really dangerous. And because it's so reactive, okay, because if something is so spontaneous, that it occurs really fast, it could be violent, it could be, it could produce a lot of heat. It will produce a lot of heat, and of course a lot of caution has to be exercised when you try to carry out such a reaction. And because of the fact that it's so reactive, it becomes non-selective, you see. So if a reaction is non-selective, that means you get a plethora of products. Chances are that reaction will have very little use in organic chemistry. And so that's why fluorination of hydrocarbons is not very common. However, if you look at the chlorination of methane in this case, you can see that it has a much lower heat that is released. You see, the reaction is less exothermic, and as a result, it's going to be less spontaneous. And the bromination, you can see that it even has much less heat that is released. So the reaction is much less reactive, much less spontaneous. And as a result, because it is less reactive, we expect it to be more selective. I'm sure you know that there is an inverse relationship between selectivity and reactivity. The more reactive a reaction is, the more selective it's going to be. I'm sorry, the more reactive a reaction is, the less selective. Because if something is too reactive, that means it's going to give all kinds of products, right? That means it's going to be less selective. But if it is less reactive, it's going to be more selective. And so you can see here that the amount of heat that is released in the case of the bromination is much less. And of course, when you look at iodination, you can see that it's non-spontaneous, and because it's non-spontaneous, it's not going to really have any use in organic chemistry. And so we can now delete or remove fluorination as well as iodination. We don't really use those in organic chemistry. Let's now consider chlorination and bromination. Now, if you look at and just like what I told you earlier, because fluorination is so exothermic, it's impractical, it's too violent, it's unsafe, right? Iodination, on the other hand, is non-spontaneous, right? It's not product favored, and as a result, it really doesn't have any application in organic synthesis. Okay, you can see that delta H here is positive, and so the reaction is non-spontaneous. However, when we begin to look at chlorination and bromination in more detail, we need to consider the chlorination and the bromination step, and we need to consider chlorination and bromination. But to be able to understand why bromination is more selective, okay, we need to look at the propagation steps that add up to give the overall reaction. Now, in the case of the first propagation step, which is the abstraction, the hydrogen abstraction, notice that it is spontaneous or for chlorine, but non-spontaneous for bromine. It doesn't happen right away. So essentially, it is endothermic for bromine, but exothermic for chlorine. And so the chlorine way is, of course, more reactive, that first step, but the bromine is less reactive. However, for the second propagation step, we see that both steps are, which is the halogen abstraction, both steps are exothermic. And so overall, even though both reactions are exothermic, right, we know that the chlorination is more reactive, and as a result, because the chlorination is more reactive, it's going to be less selective. Okay, because the chlorination is more reactive, it's going to be less selective. Okay, it's going to be more. It's going to be more. It's going to be less more reactive, and so it's going to be less selective. And because it is less selective, it doesn't have as much use in organic synthesis. Because in organic synthesis, you want a reaction that will give you strictly one product. Okay. Now, if you look at delta H for the reaction, it is more negative for the chlorination, as you can see here. And because it's more negative for the chlorination, as we said, it's more reactive. And because it's more reactive, it's going to be less selective. Okay? But then let's explain why this is the case. Now, if we look at the halogenation with the chlorination and bromination, which step in the mechanism is the slow step? Of course, the slow step is the step with the highest amount of activation energy. You can see here, this is a greater amount of activation energy compared to this. This is smaller. So the first step is the rate determining step, right? And in the case of the bromination, the first step as well is the rate determining step, right? Because it is endothermic. Okay, it is endothermic, and of course is greater than the activation energy for the second step. Okay, so you see there's a clear distinction here. For the chlorination, both steps are exothermic, but in the bromination, the first step is endothermic, while the second step is exothermic. And that's why bromination is more selective. It's not as reactive, and so it is more specific in the way it reacts, and that's why it's more selective. Now, with substrates more complex than ethane, right, multiple monohalogenation products are possible. For instance, you could have substitution at any of these hydrogens, in which case you could have a second degree substitution, or you could have a first degree substitution, depending on, you know, this could happen, see. But what has been observed is that the second degree substitution occurs more than the first degree substitution. In fact, you have 60% of the secondary alkyl halide occurring over the primary alkyl chloride occurring, you see. And the reason has to be with the rate of reactivity of the of each of those carbons. Now, I'm going to show you a table much later, which we're going to use, but essentially how I got the 40% and the 60% is, if you look at, we have 6 hydrogens at the primary position that have the possibility of being abstracted. Okay, we have 6 of them. So 6 times 1. Now this 1 is the rate of the reaction. The rate of the reaction for the abstraction of a primary hydrogen, right, is 1. And because we have 6 of them, that's why the 6 comes from. So the total rate of the of abstracting hydrogen should be 6 times 1 for the primary hydrogens. And then for the secondary hydrogens, the rate of abstraction of a secondary second degree of a hydrogen connected to a second degree carbon is 4.5, and we have 2 of them. So 2 times 4.5 plus 6, and so if you do the math, you get 40% here. You get 40%, all right? And if you do the math you get 40% here. Now, so if we have the first degree substitution to be 40%, of course, the second degree substitution is going to be 60%. That's a no-brainer, all right? And that's what is actually observed in practice. Now, for the chlorination process, the actual product distribution favors 2 chloropropane over 1 chloropropane, and the reason is because of the difference in energy, the difference in activation energy, between for the formation of both types of alkyl halides. Now, which step in the mechanism determines the reduced selectivity? We know that it's the first step because it involves the formation of the more stable secondary radical. So it involves the formation of the more stable secondary radical. As you can see here, in the first step, it involves the formation of the more stable secondary radical. And once the secondary radical is formed, it reacts with the molecular chlorine to give the product, which is the secondary alkyl chloride or 2-chloropropane, as you can see. Now, in one reaction, if primary free radical forms, and in the other a secondary radical forms. You see, and you can see because the secondary radical is more stable, you can see that it is formed by a lower activation energy. You see, it's formed by a lower activation energy, because if you look at the activation energy for the formation of the primary, you know that it's much greater. It's going to be much greater. You see. So the secondary radical is formed by a much lower amount of activation energy, okay? And that means that the reaction is going to be kinetically controlled. And also, because of the fact that the secondary radical and the primary radical are both more stable than the reactant, it's also thermodynamically controlled. You see? Thermodynamic control because you are forming more stable intermediates, and at the same time the activation energy that leads to the formation of the more predominant product is lower. You see, it's lower, and so the reaction is actually going to go through a lower activation energy pathway. Okay, so the reaction is both kinetically and thermodynamically controlled. Okay, now for the bromination, on the other hand, the product distribution favors 2-bromopropane over 1-bromopropane. The question is why? If you look at it again, the first step is the step that determines the reduced selectivity. That's a step because that is the rate determining step, right? That is a step that involves the formation of the radical, okay? And you can see this will have gone through a secondary radical, which is more stable than a primary radical, which is less stable. And so that first step is really crucial in determining the outcome of the reaction. We'll continue from the next slide.